Hi everyone. Welcome to Homer Energy's educational webinar series. I'm Marilyn Walker, Chief Operating Officer here at Homer Energy, and I'm going to be your host today. So today's webinar features our industry and component partner, American Vanadium, and the topic is modeling the cell cube energy storage system in connected and remote microgrids. We're going to begin with a brief introduction from Dr. Peter Lilienthal, the Homer Energy CEO and actually the creator of the Homer software. And then we have three American Vanadium representatives on the line with us today. Brian Beck, Vice President, he's going to give us an overview of the company and their products. Tim Yip, Sales Engineer, will walk us through modeling the cell cube product in Homer and some of the things to consider when you're doing that to get a good result. And Scott Debenham, Western Regional Sales Manager, then is going to talk a little bit more about the technology in detail.
And so what's new in Homer is we've created a new library. That's actually, we're going to keep improving that with the next release, but right as of now you can do more than you could in Homer 2, and which includes storing cost data. We have new ways to look at results. It makes it easier to export it. You can choose what parameters go into the summary tables, the optimization table, and the sensitivity results table. You can sort on any of those columns, not just on net present cost. We had a lot of requests for that. We've made it much easier to input loads if you want to just do it quickly. We have 4 standard sort of generic load profiles that are a great place to start. And getting solar resource data into Homer now is as simple as clicking on a map. We've created an API for people that have their own dispatch strategies that they want to use, and that's another capability that we're going to be expanding. We've made it much faster to do sensitivity analysis with taking advantage of multiple core processors with parallel processing. We've added a bunch of new components. We have a thermal load controller is now a separate and new component with its own capacity and cost. We've added concentrating photovoltaics. We've added a maximum power point tracker, which Homer 2 sort of assumed you have, but now if you want to, you can give it a cost and an efficiency. The efficiency doesn't have to be linear. We've added hydrokinetic, which is turbines sitting in a river that with no dam, or they can also be used in tidal currents, etc. We've improved a bunch of the components, so now you can have 10 different PV arrays with different orientations, different we've been asked for that a lot. We've made the wind turbine capability better, so you can put in different kinds of losses. We can put in maintenance schedules for both the wind turbines and the generators. We've allowed you to have minimum run times on the generators. We can have up to 20 generators now, so we're doing a lot more work with larger systems like where that becomes important. We've got a new dispatch strategy that minimizes fuel explicitly or specifically, and probably one of the most interesting new capabilities, and one that the American Vanadium is going to show some results from, is on the grid module. So we've made it and improved its ability to model grid connected batteries, which is actually the subject of this webinar. And we've also allowed you to have an unreliable grid, to scheduled outages on the grid. In the next version, in April, we'll have random outages as well. I hate to talk about vaporware, but a little bit there. Anyway, so there's a lot of new capabilities in Homer Pro, and the thing that excites us the most about it is it's a platform that allows us to roll out enhancements at a rapid rate, which we couldn't do with Homer 2. So you'll be seeing lots more enhancements every quarter. Just a little background for those, most of you are probably pretty familiar with Homer, but I like to talk about its how we've been around for over 20 years. It was really developed at NREL up until 2009 when we spun off Homer Energy. We're now up to 120,000 users and distributed all over the world, so only about a quarter of them are in the US, and really cover the world. I like to think of Homer as a way to bridge different communities within the power ecosystem, if you will. So we talk to a lot of renewable advocates that want to do 100% renewables, and we talk to a lot of utility operators who are scared to death at talk like that. So we also talk to power engineers who are used to dealing with very, very sophisticated and complicated power flow models, etc., and financiers who have their own spreadsheets. And those are very, very different kinds of models. Homer fits in between. There's a big gap between those kinds of models, and Homer fills that gap, and it also gives people a medium to communicate between these different communities of the renewable community and the traditional utility community. Our goal with Homer is to have a tool that is useful to everybody in this slide. So just very quickly, we're going to let American Vanadium take over in a second, but I'd like to talk about the different microgrid markets that are out there. There's islanded grids, which are real utility companies, but the burning liquid fuels, which are expensive. There's the energy access community. There are 1.3 billion people without any electricity at all, and another comparable number of people who have very, very part-time power and want to know how they can improve that power. The growing market here in North America, especially in the Northeast, is what we call the resilience market. Places that want power no matter what happens. If we've had some big storms where power's been out for a couple of weeks. If there's catastrophes of all different kinds, you want all your emergency services, your critical infrastructure to be up and running, and of course the military is very interested in that as well. And the sleeping giant in this market are all the unreliable grids in the world where people have backup generators. They're noisy, there are maintenance issues, etc. And renewables are now really viable in that market, but it's more complicated, and so Homer's designed to help people figure out what to do in that situation. So enough about Homer. This is really American Vanadium's webinar. They're one of our industry partners. And I just thought I'd mention the industry partner program in case there's anyone on the webinar today who'd like to know more about it. We've signed up about a dozen so far, and including American Vanadium, and we'd love to have more. So with that, I will turn this back over and let the folks from American Vanadium take over.
Great, thank you, Peter.
Okay, thank you. Well, welcome everybody. I'd just like to give you a very brief introduction to American Vanadium. We are an integrated storage company with a strategic relationship with CellCube. CellCube is manufactured by the Gildemeister Energy Solutions Company, part of the Gildemeister industry giant, really, based in Europe and in Asia. American Vanadium has this strategic relationship. We are able to, we have rights to the only US domestic supply of vanadium, which is the critical element for the electrolyte for the vanadium redox flow battery. So we are going to be talking about long duration energy storage with the CellCube. If we just go to the next slide, you will see an illustration there of what CellCube is. CellCube comes in two basic sizes. The system on the left comes in units of 10 kilowatts, 20 kilowatts, or 30 kilowatts, and up to 130 kilowatt hours of storage. On the right is the largest system. It's a 200 kilowatt power unit on the top and a 400 kilowatt hour energy module on the bottom. And then these can be just plug and play, mix and match, taking us up to multi-megawatt systems. Discharge times are 2 to 12 hours. And just like most flow batteries, big advantage is that energy and power are decoupled. In other words, we can independently scale the kilowatts and the kilowatt hours. Because of the technology, very long lifetimes, up to 20 years, capable of full depth discharges many times. So no impact on the performance or the life, that these can be taken down to zero state of charge. The cell cube has been commercially available for more than 6 years, and there are close to 100 installations globally. So we're talking about, although it's a new technology, it's a technology that's been proven, and it's been around for a number of years in various types of installations. Because it is a long duration system, ideal for things like peak shifting and load management, but it also has the capability to do all of the short-term applications like frequency regulation and voltage support. So ideal for microgrid support. With that, I'm going to turn it over to Tim Yip, who's going to take us through his Homer model.
Thank
Thanks,
you, Brian.
Tim.
So I'll start off with going over the presentation overview. So I've broken the Homer portion into 3 sections. First section is going to look over the microgrid conditions. Second is to understand how to set it up in Homer, and lastly to look into the results, and I'll add a few notes to that. But before we begin, I'd like to mention a few key points. So this presentation is under the assumption that the users listening to this webinar are familiar with the basics, and also the economic factors, they're all set to default values. So I believe the interest rate is set to a 6% default, for example. So with the microgrid example that we'll be covering today, it'll involve a PV system, a grid, energy storage with the cell cube, and a load. So generally for projects that we encounter, we're aware of the project location, the load profile, and also the grid tariff. And what we're looking for is determining the PV and cell cube sizing. So one thing to note is understanding the DC components and also the AC components. So DC, the PV is DC, which is commonly known, or what most people already know. AC components are load and grid. And special cases with the cell cube, because it's a turnkey solution, the inverters are already built in, we'll treat this as an AC component. And there's a bit of a unique procedure to understand in order to implement this into Homer, which I'll elaborate on later. So here's a quick overview of the schematic in Homer. So we'll jump into the electric load first. So here's a load profile. It's fairly generic. The the load picks up at around 8 o'clock and peaks at about 12, sustains the peak until around 5, 6 o'clock. Fairly simple, straightforward. So next we'll move on to the grid. So here's a tariff that I've set up. It's fairly simple. The price is 50 cents, as can be seen in parts of Hawaii. I've also set a demand just to add some variance. This is just the general grid tariff I set up. Some tariffs, for example, can be really complex, as seen in parts of California, where it's really seasonal dependent. It's also, there's a different pricing for weekdays and weekends as well. So if you, from some tariffs I've encountered, you could have as many as 12 to 14 different rates that you'd have to enter here. So one thing I'd like to mention is if you were to click the edit button, you'd pop into the rate properties. So for the rate properties, one thing I'd like to mention is the control parameters. So depending on how the tariff is structured and how it works, it's a good idea to have appropriate checkboxes ticked. So for this example, because in most cases there's no net metering allowed, I have checked prohibit any grid sales to prevent that. So moving on to the PV system. So here's the PV system setup, I've kept the pricing as a default value, $3 per watt. Search space I've set from 0 to 2 megawatts. I've kept the default lifetime and durating factor as well. Fairly straightforward. Then we'll jump into the GHI setup. So as Peter mentioned, one thing I really liked about the GHI is it's a lot simpler now. You don't have to do a Google search for the coordinates. You can simply go to the Home tab and then select your location. And from that, it'll pull all the necessary information from the internet. So it's a lot more simple. Next, we'll jump into the battery setup. But before I dive into how it's set up in Homer, I'd like to jump into understanding the systems that we have at American Vanadium. So as Brian mentioned, we do have 2 lines of products: the 200 kilowatt systems, our larger units, and also the smaller module units, the 10, 20 kilowatt systems. So for the larger systems, we have 3 different configurations for different durations of storage. So there's the 200 kilowatt, 400 kilowatt hour system, as you can see at the top table, the 200, 800 kilowatt hour, 200 kilowatt, 1600 kilowatt hour. So you'd get 2, 4, and 8 hour duration respectively. And in terms of scaling, for example, if you're looking for a megawatt in storage, you'd simply have 5 of the systems in the appropriate energy storage as well. So for our smaller systems, as I mentioned, there's 10, 20, 30 kilowatts, and also the energy configuration can be 40, 70, 100, or 130 kilowatt hours. So as you can see, there's about 12 different combinations that you can have, depending on your application. So now we'll jump back into Homer. So for this so for this example, because the load is about ranges from 200 kilowatts to 500 kilowatt hour, 200 kilowatts to 500 kilowatts, most likely we'll be looking into using the larger systems, the 200 kilowatt systems. And also, because of how the tariff's set up, that there's a demand cost between 12 p.m. to 6 p.m. requiring a 6-hour duration. Most likely we'll be looking into our longer duration systems. But because I'm not too entirely sure which system it is, I've entered both the SB 200-1600 and the 200-800. So for the values, the capital cost, what I've entered is a partially discounted system. So for places such as Hawaii, there's several incentives that can occur. So you could get up to 50 to 80% or even 90% discount on top of your system. So Scott will elaborate a bit more about that. The batteries I've set up, it ranges from 0 to 5 systems, so covering up to 1 megawatt. So one thing I'd like to focus on is the note here on the bottom left. So this note essentially describes how to implement the CellCube system into Homer. So as I mentioned, it's a turnkey solution. It has a built-in inverter, and because of that, all the calculations, efficiency, and the performance of the CellCubes is already included. So that being said, because of that, because of how Homer requires the CellCube to be connected onto the DC bus, you would need a converter as a result. So for the converter, you'd want to set it to 20 years life just to match it with the CellCube, and also 100% efficiency, just to make the converter aspect negligible, since the efficiency is already considered in the CellCube add-on. That being said, when you are adding or creating a microgrid, including a PV, it does add a bit of complications to it. So because the PV system requires a converter, and there is a cost and there is an efficiency loss, I recommend using an average of the two. So, for example, if the efficiency of the converter for the PV is 90%. I'd use an average between 90 and 100%, so 95% in that case. So likewise, I'd do the same for cost. So in this case, I set the converter size from 0 to 3 megawatts. 3 megawatts is fairly oversized, but I've just kept it that way for simplicity reasons, just to make sure that the sizing is sufficient. So here's a quick run overview once again of what we've just gone through. Now we'll jump into the results. So after clicking the calculator button at the top right, we'll it'll run the simulations quickly and provide a summary of the results. So one thing I'd like to mention is Homer doesn't fully optimize on the economics and performance of the battery. So I'd recommend having external models to fully understand the economics, because depending on the tariff structure, the calculations can get really complex in terms of optimizing the system performance. For example, in some days you maybe want to charge the battery up to 50%, and just to ensure that the demand cost is fully reduced. But that being said, Homer is a great usage for a quick run through and understanding just the sizing and just how the performance of the battery and the microgrid would look like. So I'll quickly jump into one of the results. So clicking the first result, you go into the simulation results. So one thing I find that is really powerful in Homer is the DMAP. So with the DMAP, it's a quick 5-second overview of just understanding how the performance of the cell cube runs through in this simulation. So as you can see, there's a lot of color variance. So because of how robust the cell cube system is, 20,000 cycles, 20-year lifetime, what we'd like to see ideally is a lot of color variance from red to black, so 100% state of charge to 0% state of charge. So as you can see, this DMAP pretty much indicates that. So at around, I think 12, so yeah, around 8 o'clock or so, the battery starts gets fully charged by noon and starts discharging as it's required to provide for the load. And one thing I'd like to mention is the table box in red here. So the autonomy and lifetime throughput can be a bit confusing, so I just want to clarify that the autonomy, both of them, they indicate the full charge and discharge cycle. So by that I mean if the autonomy was 10 hours, it would include maybe 6 hours of charging, 4 hours of discharging, and likewise for the lifetime throughput. So now generally I look through the PV tab as well, and also the grid tab, just to for the DMAP, just to see just for a logic check on the performance of the systems. So for the PV, it's running as expected. There's a lot of sunlight starting at around 8 and peaking at around 12 and dipping at right before around 4 to 5 o'clock, and that's when you'd want the battery system to kick in. So for the grid, I won't get too much into detail about the table because the information I entered is fairly generic. One thing I'd like to mention is a DMAP. So just to confirm the performance of the microgrid system, you can see that there's not much usage of the grid between 12 to 6. So as I mentioned, Homer doesn't fully optimize for demand costs because some tariffs can be really complex and requiring battery charging overnight. But in most cases, you can see it reduces demand costs. So one thing I also really like using is the plot function. So here's a quick plot of 2 ideal performance days of how a microgrid system works in conjunction with the cell cube system. So On the right, there's various different information that you can really plot. So the four that I really recommend using is the AC primary load, which is in a pinkish red, grid purchases in an orange, total renewable power output in yellow, and also CellCube FB 200-800, which is in light blue for the state of charge. So as you can see with how the graph looks like, PV picks up at around 8 o'clock, it reaches its peak at around noon and starts dipping from there. And following, you can see the CellCube system, it starts picking up as soon as the PV energy surpasses the load. And it starts discharging when the PV dips below the load. So this graph pretty much confirms an ideal function of how the microgrid would be expected to perform. So now I'll pass it to Scott to elaborate more on the SGIP and how the incentives work.
Thank you, Tim. Yeah, in California there are incentives that target energy storage. And if you look at the bottom, the third row from the bottom, we've got advanced energy storage at $1.46 per watt. Now this is a program that is administered by the utilities, where they collect money from ratepayers and set it aside and provide it back for projects that meet the requirements. And the requirements in California for this program are that it be a minimum of 2 hours of energy storage. So the goal of the program is peak load reduction. So $1.46 per watt is $1.46 million per megawatt. So it's a substantial amount of cash incentives that can help make a project go, and it can include, or it can pay for about 1/3 of the storage costs from the California state incentives. And if you can go to the next slide, it shows that it's a tiered diminishing schedule. And what I mean by that is the first megawatt provides 100% of the incentive, so 1.46 per watt, where the second megawatt is half of that, and the third megawatt is half of that again. So it's sort of an optimization exercise here, where the sweet spot is really about one megawatt. So that's typically a starting point for optimizing the state incentives. Now keep in mind that the state incentives are just one factor to optimize. There are others, as Tim has mentioned. And the table down at the bottom shows that the incentives decrease per year. For the emerging technologies down at the bottom, which includes energy storage, they reduce at 10% per year. So this is it's a first-come, first-serve program. It's expected to diminish over time as the costs of storage drop. So if you go to the next slide, I'll briefly describe some of the federal incentives which apply on top of the state incentives. So for the federal tax benefits for storage consist of two components. One is the 30% investment tax credit, known as the ITC. So that's 30% of the installed costs as a tax write-off, which is substantial. The second one is depreciation. In this case, the Modified Accelerated Cost Recovery System, known as MACRS. Now that's a very accelerated depreciation schedule over about 6 years, which on a net present value basis can equate to 30 to 35% of the installed costs. So if you look at the ideal situation, you've got federal incentives, two federal incentives that add up to about 60%, and the state incentive, state cash incentive, which is about 1/3 of the cost, which can get you over 80, as high as 90% in the ideal situation. Now, one of the keys for this is that the storage must be coupled with solar or wind, and by coupled, they mean that per the IRS requirements, that 75% of the charge energy must come from the renewable generator as calculated on an annual basis. So the idea is that you have less than 25% of the charge being done by grid energy. So you have to keep that in mind for the sizing and the operation of the storage system. So it is charged primarily with solar or wind, and limiting grid charges to 25%, again, on an annual basis. And lastly, there's a link at the bottom that describes more in detail the tax credits and the accelerated depreciation, and it describes a 75% requirement for properly coupled storage properly coupled with solar or wind. And so that's a summary of the federal and the state incentives. And these federal incentives, as I understand it, apply to territories. In other words, Puerto Rico and the U.S. Virgin Islands. So it's something to keep in mind in the financial structuring. And most of the financial people should be familiar with this, but surprisingly, some people aren't aware that storage is eligible for the federal incentives. And again, this can vary on a yearly basis with the tax code, but it's something to keep in mind because, as you can see, these incentives are substantial. So that's my summary on the state and federal incentives.
Great. Thanks. So I'm going to make myself the presenter again because we've got lots of questions here. And we will get started answering those. So let's see. Let me pull this up here. Okay, the first one, it's actually, I'll put them together, is this: how often does the cell cube stack need to be replaced, and also how many years the membrane needs to be replaced?
Yeah, I'll take that. The life of the system is around about 20 years, and one of the reasons that there is such a long lifetime is that we're dealing with the vanadium element. And in most energy storage systems, you have two dissimilar elements. So each time that you charge and discharge, you get some sort of you get a chemical change of state happening, and that normally leaves some sort of residue behind each time that happens, and it's that residue that tends to build up over time, which tends to kill a battery. Now, that happens to some extent in the vanadium chemistry, but only to a very small amount, because you're not dealing with a chemical change of state in a vanadium redox battery. You're actually dealing with just changing oxidation level of the vanadium element. Vanadium is a peculiar element. It can exist in 4 valent states, and we use those valent states, 2 on the positive side and 2 on the negative side. And so all we're really doing is just changing the oxidation level. So that's the reason we get these very long lifetimes. And because, as I mentioned before, you can take these things down to 0 state of charge without any impact on life. So the actual life of the battery is really determined by its age, not its performance. And so you would expect to see the membranes lasting around about those 20 years. And since that really is the important element of the cell stack, and then you would expect to see the cell stacks lasting for that length of time as well.
Great. Brian, we're getting a lot of questions about cost.
Okay.
You know, asked in various ways, how much is this cost per kilowatt compared to other battery technology? So maybe if you could talk a little bit about the difference in this technology and where it has advantages and how to help people understand these costs.
Yeah. Okay. Certainly cost is always an important issue, but there's 2 caveats I need to explain. One is, we mentioned at the beginning that a flow battery separates power and energy, or power and duration. In other words, we can have as was shown in the presentation, a 200 kilowatt battery with 2 hours or 4 hours or 8 hours. So then, by definition, a dollar per watt number really doesn't make any sense, because it's obviously going to be different for those different durations. So you have a very non-linear set of metrics in the cost equations. And also, we're dealing with new technologies, and just like all new technologies, we're on a declining cost curve. So the danger is that by using a single dollar per, we can't use dollar per watt, as we've mentioned. So the next thing that you would look at is using maybe a dollar per kilowatt hour number. But those are very non-linear, so there isn't one magic number that would go across the board. And the danger is that you carry that number around in your head and you try and apply it to, you know, a system that lasts for 4 hours or 8 hours, or that's 1 megawatt big or 10 megawatts big. You know, there isn't just one number for that. Now, I know that people will roll their eyes and say, well, you know, we're trying to hide the cost. We're not, because it's you know, we can easily get to the cost number very quickly. if you're looking at a multi-megawatt, multi-hour system, then we're seeing total system costs coming down to below $1,000 a kilowatt hour. And I must emphasize that we're talking here about system cost. Typically, in solid-state batteries, you have a number of cost levels. You're looking at cell cost level, and then you're having a rack cost level, and then you're having a system cost level, and then when by the time you've added the all the inverters and the and any necessary air handling or air conditioning, then that takes it up to an installed project cost. So when I talk about the $1,000 per kilowatt hour, we really are talking about the complete installed system cost. But I would encourage people that we're not trying to hide cost information here, but it is so nonlinear that if you have a specified project where you know exactly the kilowatts and the hours, by all means get in touch with us, and we can by return give you a system cost for that.
Great, thanks. Okay, so let's move maybe to some technical questions. Dealing with someone asked, how do you deal with the limited temperature range that vanadium batteries tend to have? What are you doing to optimize the batteries? Okay, well,
once again, when you say limited temperature range, you're really talking about the electrolyte, and its operating range is between 0 to around 40 degrees centigrade. Now these systems are in an insulated container, and so within our scope of supply we manage the whatever ambience conditions we're working in. We have systems working in Abu Dhabi, and we have systems working in Moscow. So that's within our scope of supply. If necessary, we can provide active heating and active cooling, but in most cases that isn't really necessary. As I say, it's an insulated system, and when you take it over a daily cycle, then the additional heating or cooling is not necessary. But we are aware that we need to keep that electrolyte within that operating range, and as I say, that is part of our scope of supply. And I think that really is a good point, just leading on to the fact that it is a system that's built on a modular basis, and one of the advantages of that is that all of the variables that you would associate with manufacture are actually dealt with in the factory. They're not transported to site, where if you're sort of putting one of these things together on site, you bring all those manufacturing variables on site and you're having to worry about them there. By going to this type of modular system, you can have a lot more confidence in the fact that the system is being manufactured to very strict engineering standards.
Great, thanks. Okay, I'm going to put a question for Peter. We got, the efficiency of vanadium batteries are a function of state of charge and instantly discharging or charging power. Have you simulated this phenomenon in Homer?
Marilyn, the webinar software announced that you would giving me the control in the middle of your question. Could you repeat your question?
I'm sorry. The efficiency of vanadium batteries is a function of state of charge and the instantly discharging or charging power. Have you simulated this phenomenon in Homer?
We have a round-trip efficiency in Homer, and it's constant. Actually, it feels to me like Brian should weigh in on that question, because I don't know to the extent to which the efficiency does. I mean, at higher powers, you'd expect any device to have higher I2R losses, but I'm not sure how significant those are. Brian, how significant is that?
Well, it's a good question, because the fact that you can take a system down to zero state of charge, and if we think about it on simple terms, if you are discharging into a constant load, then like all batteries, as you discharge, the voltage output tends to drop, and so if the voltage is dropping, it's going to be at its minimum when you're down to zero state of charge. If you're feeding a constant load, then by definition your current is going to increase. And since losses are proportional to I squared, to the square of the current, then you would expect your losses to be much higher at zero state of charge than at let's say 90% state of charge. There is a range, overall in a typical daily cycle, and you take this into account when you're actually sizing a system, because you don't want the system too big or too small. So you're looking at a round trip efficiency that normally comes out at around about somewhere between 70 to 75% for one of those types of discharge cycles where you're taking it down to maybe 5–10% state of charge and back up to to 100% state of charge. So I don't think it's we don't actually do dynamic modeling of that within Homer, but we do take into consideration that 70–75% is a pretty good number.
Yeah, it's actually, if I may jump in with a comment about sort of modeling philosophy. Homer is designed as an optimization and decision analysis tool where you're looking across hundreds or maybe thousands of different possible configurations and possible scenarios. So our goal is to allow you to look at many different configurations and scenarios and compare them to each other. So we put a premium on speed over putting in all of the details. So what we, especially with batteries, we find that there's a lot of phenomenon with batteries that you could model, but would require a lot of iteration within each time step, and you'd never be able to do the thousands or tens of thousands of simulations that a typical Homer run involves. So there's a trade-off. If you want all that detail, you're not going to get the optimization and decision analysis capabilities, and that's just our modeling philosophy.
Great, thanks. So we have a question about markets. Is this available in the U.S. only, the EU, or where?
Yeah, American Vanadium is, as I mentioned, has a strategic relationship with the manufacturer Gildemeister, and we tend to operate our business within the North American market, and or projects that originate, in other words, that are being engineered in North America. But however, by all means contact us, because we will pass your details on to Gildemeister, and they are active in all continents. As I said, they're only really a recent entry into the US market. Most of their work has been in Europe and Africa and Asia.
Great, thanks. Okay, I'm going to actually answer this question. Is there special training to learn how to install? Well, actually, I won't do the install and design. So I'll push this back to our American Vanadium friends. Are there training to learn how to install and design your systems using these batteries? How do you deal with that?
Yeah, but training to design. Well, we obviously like to encourage you to use Homer, because Homer's embedded now. So that's a good starting point. And then once we get one identified, then we can work with you to tune up the final design. And then as far as supply and installation, that is done by Gildemeister in conjunction with American Vanadium. And then within that installation and commissioning process, there is on-site training for local technicians and technical staff. These systems are remotely monitored, and they're a pretty simple concept, so they aren't maintenance intensive, but obviously it always is a good idea to have somebody local who is familiar with the system, and we provide training for that.
Great, thank you. And I wanted to follow up by just saying that we are in the process of getting ready to release much more advanced training modules for Homer. So, and one of them will be storage systems in general, and look at that. So we're looking forward to that, and that should work well with that. Is there a cell cube product for electric vehicles? It's a question.
The quick answer to that is, yeah, the quick answer is not for the vehicle itself, but the cell cube is ideal for charging stations. If I think we have some examples of that maybe on our website, but so it's ideal to be used for charging stations. But one of the features of the vanadium redox flow battery, it has many good features, but on the downside it is not as energy dense as some of the other solid state batteries. So it's not ideal for putting into a vehicle.
Great. So here's another question. For a typical load profile, will the maximum charge and discharge rate support more than one deep cycle per day?
Oh yes, yeah. It typically, as a rule of thumb, there will be about a 1.4, 1.5 to 1 charge-discharge ratio. In other words, if you charge it for 6 hours, you would get about 4 hours of discharge. So that means that you've now taken up 10 hours. So you'd certainly get 2 full cycles per day. On the other side of that coin, we have had vanadium redox batteries working in conjunction with wind farms where they sit at 50% state of charge and then go through hundreds of minor discharges per day, just absorbing and discharging, filling in the blanks on a wind farm. So it can do the full deep cycle, or it can just sit there and work as some sort of energy buffer.
Thank you. Great. We're getting so many good questions. I'm trying to combine some of them, but a couple people have asked about frequency regulation and using the vanadium batteries for frequency regulation.
Yeah. Frequency regulation is often seen as what's known as a power application. It's a short duration application. It can be met by most batteries and by flywheels, but it's also because we have the capability to do long duration systems. That doesn't mean to say that that's all we do. We are able to do those very short discharges and charges. So the advantage of the vanadium redox flow battery is that it is very flexible, and so you can have multiple applications from the same battery. In other words, you can be participating in let's say a ancillary services market where you're providing frequency regulation services. You can also supply voltage support services because we can provide kilovars. We can provide a black start capability. We can peak shift. We can make the solar peak coincident with the load peak. That may be a 4 or 6 hour difference. And we can do that all out of the same battery. All we have to do is just calculate how much electrolyte we actually need to put into the system. And as you saw during Tim's presentation, that could be a 2 hour or 4 hour or up to 12 hours of electrolyte in those systems. So yeah, we can certainly do those short-term applications as well as the longer-term applications.
Marilyn, I'd like to jump in with 2 questions that I've noticed. One's very Homer-specific, and one I'm going to pass back to Brian. But the Homer-specific one has to do with this AC and DC bus issue. So right now, we don't have the capability to put a battery on the AC bus. We're hoping to change that. And Tim went over this, but I was just looking at the number of questions about this. I thought I'd jump in. So because of that, the way you can model an AC battery is go ahead and put it on the DC bus, but make the inverter irrelevant. Make it bigger than it could possibly need, no cost, 100% efficient. It will have no effect on the modeling. And as far as your results are concerned, the results will be the same as if it was put on the AC bus. The one downside to that some people have noticed is, well, you've got your PV needs an inverter as well. And I should have mentioned this in the beginning. You can put the PV on the AC bus, and now with this is different than Homer 2. In Homer Pro, that means you've got a dedicated inverter for the PV, and it can have its own cost and its own efficiency. So you actually can have an inverter for the PV separate from the inverter for the battery, so that solves that problem. I think that most people were focusing on, and this trick to that is put the PV on the AC bus. Within the PV module, there's a dedicated inverter. The other question I'd like to throw back to Brian, because I judging from questions that I'm seeing, I think there's some misunderstanding. And there was one question about limiting the range of state of charge on the cell cube, and I thought you should talk a little bit about what's it. My understanding is there really aren't those limits. Could you talk about the cell cube's ability to operate between the full 0 to 100% state of charge?
Yeah, the system itself is a pretty simple concept. It is although it's an energy storage device, it looks very much like a fuel cell in its construction and just the way it's put together. So what we're actually doing is running a fuel cell with liquid electrolyte. So it's a very benign operating environment. It's being cooled by this, constantly being cooled by this liquid electrolyte, and then the electrolyte is just stored in separate tanks, and it's the size of those tanks which determine how long or how much duration you have of battery. And state of charge is pretty much self-limiting. We can take it down to 0 state of charge, and we can take it back up to 100% state of charge. Because of round-trip efficiencies, I mentioned there's about a 1.4 to 1 ratio, charge to discharge. But the device itself is pretty simple. The intelligence comes in the interface with either the microgrid or the actual grid, and that is in the inverter system. But the battery itself and the battery management really just works on a simple principle. If the voltage of the cell stack is higher than the load, it will discharge, and vice versa. So all you're trying to do is manage those with the battery management system. But certainly it's capable of using that whole range, and I think people who are familiar with battery systems realize that that's not always possible with other types of technology.
Thanks, Brian. It's 11 o'clock here in Boulder and 1 o'clock on the East Coast, and I know people have things to do. We did not get to all of your questions, and it's great to see so many questions. And we have set up this forum. This same link will also be in your email. We are going to try to get to the questions. I know that American Vanadium wants to, get you the information, and Homer Energy certainly wants you to get the information around, around the Homer questions. So we really appreciate those of you who are emailing us right now that you got up at 4 and 5 a.m. We have recorded it. We are going to make that available as well. And so thank you all, and we'll continue the discussion. And I'm going to end the broadcast.